Hi, in this video, I will talk about magnetism. We will learn what magnetic fields are and how they are produced. And we will also move to magnetism in matter. So let's get started. All magnets have two opposite poles. I think you know this since elementary school. So all magnets, they have two poles called north and south. So like poles repel, so just like here, north and north or south and south, they repel each other. And the opposite poles, they attract each other, as you can see here. So if you have a magnet and if you cut it into half or break it into half or smaller pieces, in this case, two pieces, then you again get magnets with, again, two poles. So you never get only south or only north. So all magnets have two poles. Compass needles, it's here, and again, I'm sure you played with compass needles at some point in your life. So compass needle is a small bar magnet. So this part is actually a magnet, and its north end, which is shown in red color, it points in the direction of the magnetic field created by the large magnet here. So this large magnet, it creates magnetic field around itself, and the compass needle, the red part, it always shows in the same direction with the magnetic lines. For example, magnetic lines, they go in south here, so the red arrow shows right direction. Here, magnetic field lines are in this direction. So here, as you can see, the compass needle shows to the left. Magnetic field lines exit from the north pole of a magnet and enter at the south pole. As you can see here, they exit from here and they go in to the south pole. And in this figure here, what we have is we have iron filings, so basically small iron pieces. So they are also like small magnets. They're aligned according to the large magnet's magnetic field lines, as you can see here. So these are the magnetic field lines. If you scatter some iron filings here, they will be aligned in the same directions with the magnetic field lines. So compasses show a geographic north pole of the Earth, because magnetic fields of the Earth are towards there. So inside the Earth, there are certain metals and plasma, so they create some, because of the currents of those charged particles, they create magnetic field lines. So you can think of there is effectively, there's a bar magnet inside the Earth, and its north pole is down and south pole is up here. So as we mentioned in the previous slide, magnetic field lines, they come out of north pole and they go in the south pole. But what happens if you are at some point on the Earth and you take out your compass and look at the needle? The needle will show, it will be aligned with the magnetic field lines. So because the magnetic field lines, they go out from north and they go in south, so it will show you, the compass will show you the south pole here, but it's actually, so in terms of magnetic magnet, it's the south pole of the magnet, but this place is what we call it is the geographic north pole. So geographically, we call this part of the Earth North Pole. But in terms of the magnetic field lines, it's actually the south pole of the effective magnet that is created by the ions within the Earth. So magnetic field SI unit, the standard unit is Tesla. And there's another unit, it's called Gauss, and the relationship between them is 1 Tesla is 10 to the 4th Gauss. And here you can see a magnetic field created by different things. For example, on the Earth, you can go up to 6 times 10 to the 5th by using different devices, or coils, or maybe superconducting materials. So this is 60 Tesla, and if you have a bar magnet, it's 100 Gauss, and that means it's 0.01 Tesla. So, and the Earth itself, it has its own magnetic field, as we mentioned here, and that's actually what affects the compass. And that's a really small magnetic field, because 0.5 Gauss, it means 0.5 10 to the negative 4th Tesla. So it's a really small amount of magnetic field strength, but that's enough for a compass to, that's enough to affect a compass, so that you can find the directions on the Earth. So let's talk about magnetic force. So magnetic force causes already moving charged particles to deflect. So for magnetic force to affect a particle, here you can see that there are two conditions. One of them is that they have some velocity which is not zero, so they're already moving. If there is zero velocity, then magnetic field it doesn't create force on that particle. The other one is charged particles, so the charge is also not zero. If the charge is zero of a particle, then magnetic field does not affect it. So let's take a look at here. So we have this charged particle. It can be positive or negative. So it goes into this field, and this field, the purple field, it has magnetic field. And the direction of the magnetic field, now we will use throughout this video these two symbols. This means out of the page. So think of an arrow. So this is the tip of the arrow. So you can think of this like an arrow. So this is the tip of the arrow. So that means, so the arrow is coming to you. So if you see this sign, just like here, that means there's magnetic field here, and the direction is coming from the screen. So it's coming out of the screen and it's towards you. But if you see the end of the arrow, that means that vector, it could be magnetic field, force, velocity, it could be anything. That means it's going into the page or into the screen. So in this case, we have magnetic field lines out of the page, so they are coming towards us. Now, what happens if you send a charged particle with some initial velocity? Well, it will be deflected. So if it's charged, so if it's not charged, first of all, let's talk about it. If the charge is zero, it will just go through straight. So magnetic field will not affect it. But if it's charged, let's say positively charged or negatively charged, then it will deflect. Now, you know physics 1, from physics 1, that for a particle to be deflected, so you need a force in this direction. So here, the magnetic force, you have a magnetic force in this direction for the positively charged particle. Now, how do you find, if you know the direction of the magnetic field and the direction of the velocity, then how do you find the direction of force? Well, for that one, we have to use the right-hand rule. So the direction of the magnetic force on a positively, this is important, we're talking about a positively charged particle, is given by the right-hand rule. Notice that whenever you use this rule, you have to use your right hand. If you use your left hand, then you will get a wrong answer. So that's why it's called right-hand rule. So how does it work? Well, you make these three fingers, so the thumb, index finger, and the middle finger in this shape. So there are 90 degrees between them. And the index finger, it points, so you basically point your index finger in the direction of velocity here. So you would do this. This is your V is your index finger, and the magnetic field it's the middle finger direct in that direction. So in this case, it's out of the page, so it's coming towards us. So the middle finger is towards us, and your thumb gives you the direction of the force. So in this case, your thumb gives you the down direction, so the force here is in the down direction. And that makes sense because if you pull something that was already going to the right, and if you pull it down, well, of course, there's no agent that pulls it down, it's just a magnetic field, so the magnetic force. But if there's a force in this direction, then it will deflect down. By the way, there's no gravity here. We assume in this, in this picture, there's no gravity. Okay, what about a negatively charged particle? Well, again, for negatively charged particles, use right-hand rule, but the magnetic force, so the result here, will be in the opposite direction to your thumb this time. So what you would do is, again, you would use your right hand and find the force, but if it's a negatively charged particle, so from the right-hand rule, you find the direction of the force in the down direction. Now, if you have the negatively charged particle, then you have to consider that for the negatively charged particle, you have to invert the direction. So the force for the negatively charged particle will be in up direction. And from the figure, you can see that it's deflected in the up direction. So this is how you use the right-hand rule. Now, what are the effects of magnetic fields and magnetic forces? Well, old-style TVs, and you can try this if you have an old-style TV and also a magnet. So old-style TVs have electrons fired at the screen to produce the image. So all the time there's an electron gun at the back of the TV, and it shoots electrons on the screen to produce the image. And magnet at a close range deflects the electrons and causes image distortion in the image. Notice that the electrons are fired and they hit the screen with some velocity, right? They have some velocity. And what happens if the electrons have velocity? And if you also produce magnetic field with the bar magnet, these two gives you the force. So the force deflects the electrons, and then that causes distortion in the image. Now, magnetic field is also used in the particle collisions at CERN. Collisions, so basically at CERN, what you have is two particles, let's say maybe two electrons or two protons or one proton and one electron. They collide. When they collide at high energy, lots of new particles are produced. Some of them are chargeless and some of them are positively or negatively charged. So collisions of two particles at CERN produces many subatomic particles. There's magnetic field applied in the detector, so that's an external magnetic field. And so the charged particles, paths, are curved due to the magnetic force. You can see that the paths are curved, and indeed, by using the curvature of these paths, you can determine the masses of these particles. Now, electrons, so they are negatively charged. So there's a cathode ray tube here. The electrons coming straight. The reason that they are seen blue is because there's a gas in the tube. And if you approach with the north end of the magnet, they are deflected down. And if you approach with the south pole of the magnet, they are deflected in the up direction. So, and the direction of so we know the electron, they are coming in this direction. So this is the velocity. And now we know the magnetic field. If you're coming with the north, then these are the magnetic fields. or if you are approaching with the south end, these are the magnetic fields. Now, you can find the direction of force by using your right hand. So at this point, I want you to use your right hand, use the direction of the velocity. In this case, it's there in this direction. So the magnet is in this case, in this direction, magnetic fields. And find, so of course, in this case, the magnetic field is in this direction. So find the direction of the force in each case. Now you are going to use your right hand rule, your right hand, but you have to be careful because we have electrons, they are negatively charged. Whatever you find, whatever direction you find for the force, at the end you have to invert it. So for example, if you find the force in the up direction from the right hand rule, then the correct answer is down direction. Why? Because we have negatively charged particles here. Now, Earth's magnetic field, so we talked about it. Earth has its own magnetic field. They go out from the South Pole and they go in the North Pole. And those fields, they protect us from the charged particles coming from the sun. So when a solar flare happens, so it's a kind of explosion, and charged particles from the sun, they approach to Earth. So they go in this direction. Now, the particles have charge. They have also velocity. And the Earth has its magnetic field. So again, what happens when you have all of these three? Then you have a magnetic force. Now, this magnetic force, it actually makes those charged particles to go away in these directions. So the Earth is protected by its own magnetic field. So these particles, they don't hit the Earth directly. So that's a good thing for us. So what happens is these charged particles, they actually go in this direction to the North Pole and the South Pole. And the result is the northern lights and the southern lights. So these charged particles, they produce these lights, and here it's also called aurora oval in the north and in the south. So by means of these magnetic fields, we are protected by the dangerous charged particles coming from the sun, and at the same time we have these beautiful scenes produced because of the magnetic field. Okay, here's an exercise. A positive charge enters a uniform magnetic field as shown. What is the direction of the magnetic force? So this is the velocity. Okay, now in this case, you see a cross, so that means magnetic field lines go into the page. So your middle finger should show into the page. Your index finger should show to the right. So if you do that, what you find is the force turns out to be in the upward direction. So the magnetic force is, so my thumb gives the upward direction. Now, is this a positive or negative particle? It's a positive particle. So I don't have to flip or invert the direction. So that should be the answer. So the answer is the upward direction. So the force will be in the upward direction. Okay, in this case, the direction of the magnetic field is not given, and that's actually the question. So a proton beam enters a magnetic field region as shown. So because it says proton beam, we have to, again, consider that it's a positively charged particle. And it enters in this direction, so that's the velocity. Now it's deflected in the up direction, so that means now the force is in this direction. when you do this calculations or when you try to find the direction of the force, consider this part, not maybe this part. So only consider the initial position here. So this is the velocity, this is the force because it's deflected in the up direction. Now, now have your thumb point in the up direction, have your index finger point to the right. So what do you find? If you do that, you will find that the magnetic field is your thumb. It shows into the page. So the magnetic field we find from the right-hand rule, it's into the page, and the symbol for into the page is cross. So the answer is negative z direction, which is into the page. Okay, so now we know how to find the direction of the magnetic force, but what is the value of that force? Now let's find it. So this is the formula. So the magnetic force here is the charge times velocity. This is cross product. This is cross product times the vector magnetic field. Notice that the velocity and the magnetic field, they are vectors. And here Q can be negative or positive. Now, this is a vector. So force is a vector, but if you ask what is the magnitude or strength of the magnetic force, then it's QVB times sine theta, and that theta is the angle between V and magnetic field. So V is the velocity and B is the magnetic field. So for example, you can have magnetic field lines in the up direction, and V can be, for example, like maybe in this direction. So there's an angle between them. So that angle is this angle here. And from here, you can see that when B and V, when the velocity and the magnetic field, when they're in the same direction, so that means, what it means is you have a charged particle that goes in the same direction as the magnetic field, then what happens? Well, the theta, the angle between them is 0. So you would write 0 here, and sine 0 would give you 0. So in this situation, then the magnetic field, magnetic force becomes 0. And when does it become maximum? Well, it becomes maximum when the angle between the magnetic field and the velocity is 90 degrees, because sine 90 degrees gives you 1. So we talked about how to find the direction of the force. You use the right-hand rule to find the direction of the magnetic force on a positively charged particles. And again, if you have a negatively charged particles, again, use the right-hand rule, but whatever you find as the direction of the force, then just take the inverse direction, and that would be the correct one for the force for a negatively charged particle. So magnetic force on a charge point particle, we learned that this would be the formula and the magnitude. So if you're not interested in the direction, but just the magnitude, so it will be this. So this cross product would produce sine. Remember, we had dot product for the electric fields or for other things. When you have dot product, you have cosine, but for the cross product, you have sine. So in these three situations, let's start with this one. The magnetic field lines are to the right. If the particle moves to the right, then there will be no force, because in this case, sine theta would be sine 0, because B and V, they're in the same direction. Remember that theta is the angle between B and V. So in this case, sine 0, so sine 0, I keep making theta, sine 0, and that gives you 0. So there's zero force in this situation. The maximum force, again, occurs when the magnetic field and the velocity, when they are perpendicular to each other, which means 90 degrees, sine 90 degrees gives you, it gives you 1. So you get the maximum force in this situation. And if there's an angle that's neither 0 nor 90 degrees, then again, you would write the angle here. So for example, if it's 30 degrees, then you would have a term as sine 30. So let's talk about cross product. So if you are given the angle, then you don't have to use cross product. You can use just this formula with the angle. But if you are given two vectors, such as these, like v, velocity vector, and the magnetic field vectors, then you have to use the rules of the cross product. To calculate the cross product of two vectors, let's say a vector, so it has the component x component, y and z components, and x hat, y hat, z hat, these are the unit vectors, and the b vector. So we need to use, if you want to calculate the cross product, which is a cross b, so these can be the vectors. So a cross b would give you the c vector. So you have to use these rules. So we have a couple rules here. And the order of unit vectors, order of multiplication, it does matter. So it's important. As, for example, x cross y gives you z, but y cross x, the same thing, but the order is reversed. It gives you negative z. And one thing that you can notice that x cross x, y cross y, and z cross z, they give you 0. Why? Because if these two vectors, they are in the same direction, what happens? You get sine 0, and that sine 0 kills the, so it basically gives you 0. Now let's do this exercise. Let's say the velocity vector is this, and the magnetic field vector is this. So find the magnetic force by using this formula and assume that the charge is 1 coulomb. So what we are going to do is we will write V first, this one, and we will put a cross sign and we will write this one, which is B. So this is V vector and this is B vector. And again, this order is important. If you do B cross V, it will have a negative sign. So this order is important. Now what we are going to do is we will multiply. So we will distribute like this and then multiply these and these. Well, we will do not multiplication, but cross product. Okay. So the numbers are multiplied. 5 times 1 is 5. And so from here we will have x hat cross y hat, which is here. For the second one, so 5 times 4, it's 20. And we will have x cross z, x cross z. Now for the other ones, so there's negative 3 multiplied by 1 here, so it's negative 3 here. And we have y cross y here. And for the last one, negative, so this times this is 12. And we have y cross z, z hat. Okay, so this term is already 0 because here is the rule. For x cross y, now let's look at the table. X cross y is z, so we have 5z. X cross z, let's find it. X cross z is negative y. So now here we have negative 20y. Y hat cross y hat is 0. And so we have a negative sign here, which is here. And y cross z is positive x hat, which is here. And if you want to rewrite this in the alphabetical order, then This is the answer. So notice that the cross product of two vectors, you always cross product two vectors, and the result is also a vector. But if you remember the dot product, it was different. You would dot product again two vectors, but the answer would be just a scalar, not a vector. Okay, so let's compare the electric field and the magnetic field, or the electric force and the magnetic force. So what are the differences? First of all, when we learned about electric field in the previous lectures, so a positively charged particle in the electric field. So here what's shown is we have a positively charged particle. It has an initial velocity in this direction. It's in the electric field, and the electric field direction is down. Now, what happens? So what is the force on that charged particle? If you can remember the formula, the direction of the force, electric force, it's basically in the direction of electric field for a positively charged particle. So the electric force is in the down direction because it's the direction of the electric field. And you can again look at the formula. The electric force does not depend on the direction of motion or speed. So whether this particle has velocity or no velocity, it doesn't matter. The force is independent of velocity, and it's in the direction for positive particle, it's in the direction of the electric field. Now, when you come to magnetic field or magnetic force, so let's think about now magnetic force. A positively charged particle in a magnetic field here is shown. A magnetic field is in the down direction. Now, what happens is, so if the particle has initial velocity in this direction, now at this point, use your right hand. So this is your index finger for velocity. The magnetic field is down, so your middle finger shows down direction. What you find by using right hand rule, you find there is a force in this direction. Now, so what will happen then, because there's a force, the particle its path will be deflected. Now at this point, now the velocity is in this direction. Magnetic field is again down. Now use your right hand at this point. What you will find, the force is this direction now. And at this point, the force is now this direction. So what happens is the magnetic force, it makes the charged particle go in a circle. And the other thing is, the magnetic force, it depends on the velocity vector. So if you have a particle that stays here with zero velocity, then there will not be any magnetic force on this particle. So that's definitely one difference. And the other difference here, so here you have the force in down direction. So what it does is it makes the particle accelerate in the down direction. So in these problems, in these figures, assume that there's no gravity. So this particle, it picks up some velocity in the down direction, and you can see that this component of velocity is the same, but now it's picking up some velocity in the down direction. We can call it Vy, and this one may be Vx. So the velocity is increasing here. You can also compare the magnitude of this vector and also the magnitude of this final velocity vector. So, but here, if you look at the velocity vectors, they don't change. Well, their direction changes, but the magnitude doesn't change. So the speed does not increase because of the magnetic force. The magnetic force only changes the direction of the motion. So B field does not increase kinetic energy. So that's interesting. So the magnetic force, so electric force It acts on the particles regardless of their velocity, even if they have no velocity. On the other hand, the magnetic force acts only if there is velocity, non-zero velocity. So electric force, it increases kinetic energy because velocity is increasing. But the magnetic force, it does not increase kinetic energy. It only changes the direction of the velocity. And remember, kinetic energy is 1/2 m speed squared. So this, because the speed is not changing in the case of when there's magnetic force, the speed doesn't change, only the vector velocity, the direction of the speed changes, or the direction of the velocity. And because speed is constant, kinetic energy is constant in the case of, in the presence of magnetic force. Okay, so now in the previous slide, we talked about how a particle can go in a circle without its speed, without its speed changing. So as you can see, the speed is the same in all cases, only the direction changes. So in circular motion, what we have is, this is from physics 1, Newton's second law for rotational motion. What we have is, so instead of F equals ma, we have F equals ma centripetal. Centripetal force is the force in the circular motion that's towards the center, and that force is actually what keeps this particle on the circle path. And the definition of centripetal acceleration, it was v squared divided by r. Now, this force in general, it could be, for example, in the case of Earth and the moon, it could be, so we can have Earth here, we can have moon here, and this would be a gravitational force. Or you can have a toy train here, and you can run it, and you can also tie a string and fix the string here. In this case, the force could be, it would be the tension force. But here what we have, this force is the magnetic force, because there's velocity, there's charge, it's positively charged, and there's also magnetic field, and we will have magnetic force. Now, what is the magnetic force? We learned it. It's QVB. We also have sine theta here, but the angle between the velocity and the magnetic field is 90 degrees here. Why? Because the magnetic field is out of the page, it's coming from the screen towards us, and the velocity is in the up direction, so they have 90 degrees between them, and sine 90 is just 1, so that's why I haven't written it. So this is the magnetic force. Now, so here, then I have to plug in magnetic force. So then this becomes QVB equals mv squared r. Now, one of these v's here cancels with v on the left-hand side. So what's left is r, the radius, which is the radius of this path, is equal to mv divided by, and m is the mass of this charged particle, q is the charge of this particle, divided by the magnet, so q times magnetic field. So if you want to relate the mass of the particle, charge of the particle, its speed, and the strength of the magnetic field, then you would use this formula. And again, notice that there's really nothing in the center that, this charge is not connected to any kind of rope or anything. It's just the magnetic field that keeps it in this circle. So, of course, that idea is used in practice. So mass spectrometer, that's something used in the labs. It's used to separate different isotopes of the same ions from a mixture. Different isotopes means you have the same element, they have the same number of protons and electrons, but the only difference is they have different numbers of neutrons. What's the contribution of neutrons? So they don't have any charge. The only contribution they have is the mass. So different isotopes, they are the same elements, but because of the neutron content, they have slightly different masses. So in this exercise, you have, let's say, 2 isotopes of uranium, and they are sent into a mass spectrometer with speed 1.05 10 to the 5th meter per second. So what is the reason for doing this? Because so you send them here at this point, and they will end up at different points, so that you can put some let's say some collectors at these 2 different points, and you can collect uranium 235 on the left bin, and you can collect the other isotope 238 in the right bin. So initially they were mixed here. So this mass spectrometer, it actually uses the mass difference and the magnetic field to separate them. So now in this case, finally, you would have these 2 isotopes separated in 2 different bins. So, and of course, you need magnetic field so that their path is curved. And the other thing that you need here is, so normally any element, it has the same number of electrons as the number of protons they have. So they're usually, normally neutral, not charged. But for the, if you remember the magnetic force, it was QVB, so they should be charged. So how do you make them charged? You basically strip one of the electrons they have. So so in this case, they are singly ionized, which means you take 1 electron from each. And what happens when you take 1 electron? They become positively charged. And what is the amount of charge they have? Well, it will be the amount of electron, or well, it will be the amount of this fundamental charge, which is actually the charge of a proton. So now, because they have 1 extra proton than the amount of electrons they have, so the charge is the charge of the proton, which is this number. Now the question is, find D in the figure. So what is the difference? What is the distance between the points where each isotope falls in? They have different paths. Why? Because if you remember this formula that we derived in the previous slide, their initial velocities are the same, charge the same, magnetic field background is the same, but they have different masses. So because they have different masses, they will have, so these paths, they will have different radius, different radii. If you use this formula for the isotope 235, this is the radius, and for 238, this is the radius. You can see that they're slightly different. And so then this distance is 2r235. So this distance is, so in this case, 34.1. And from this point to this point, so it's this distance, you have to take 2r, 2 times radius, because this is like the circle, this is the radius, and this is 2r for 235. And for the larger circle, you have to take 2r238. And if you take the difference between them, you will find D to be 1 centimeter. And that separation is enough to collect 2 different isotopes. Okay, here again a relevant exercise. 2 particles of the same mass enter, so the masses are the same. Enter a magnetic field, background magnetic field is the same. with the same speed, and these are the same, and follow paths shown. So two particles, they go in from here, they follow different paths. Which particle has a bigger charge? So we are looking for bigger charge. So if Q is large, and because it's in the denominators, the R value for the bigger charge, R value will be small. So we are looking for the path that the particle took, the path that has the least radius or the smaller radius. And in this case, it's this one. So the one that the particle that has the bigger charge, it gets more curved because it feels more force, more magnetic force, because it has more charge. And since it's deflected more or curved more, then its radius becomes smaller. So the correct answer is B. Okay, so let's talk about now helical motion of a charged particle. So helical motion is the motion like this. Now in the previous case, if you remember, let's go back here or even here. So the particle, the velocity vector was perpendicular to the magnetic field vector. So the particle will go like this, always at the same place, making circles. But if there's any initial angle between the velocity and the magnetic field, let's say if the velocity was more like this, then in this case, this particle would make a helical motion like this. So it would be making circular motion on this plane. On this plane, it will be making circular motion if you think about the shadow here. But in this direction, it will be also moving. So that's called helical motion. So in this case, what we have is the magnetic field lines in the positive x direction. The initial velocity is not on the z-y plane. It has a component in z direction, but it also has a component in the x direction. If the velocity was only on the z-y plane, which means only in this direction, then it will just make a circular motion here. But as you can see, it has also x component. So now the z component is perpendicular to the magnetic field. So this z component and the magnetic field, they are perpendicular because z and x, they are perpendicular. So there will be a circular motion in the yz plane. So this is the yz plane here, or you can extend it here. So on this plane, there will be circular motion. If you think of the shadow of this whole motion on yz plane, there will be circular motion. And second, Vx is parallel to B. So there's also Vx, which is parallel to B. So Vx will not change because there's no force in the x direction, because the angle between Vx and magnetic field is 0. So then there's the force, magnetic force, is not in the x direction. So hence the particle will move with constant speed Vx in the x direction. So the combination of these two effects gives you the helical motion. Again, the z component makes it go in a circle on the z-y plane. That's part I, the first part. And the second part is the x component of the velocity makes it just gets translated in the x direction, or go with constant speed in the x direction. So combination of these two results in helical motion in this direction. Okay, what we have here is, now let's go to wires. You have a wire and there's a strong magnet here, and let's say the magnetic field is in this direction. So when you turn on the switch, current goes through the wire, and when current goes through a region where there's magnetic field, it feels force. So as you can see that in one direction, if the current is in one direction, it goes up. If the current is in other direction, which happens when you push the switch in this direction, the force now is down. So before, what we did is we talked about magnetic force on point charges, positive or negative. Now what we are doing in this section, we are interested in the magnetic force on the current carrying wire. So why is this happening? Because, well, if you think about it, if you have a current, then the charged particles are flowing through the wire. When you have charged particles, when they flow through the wire, that means they have some velocity. And when there's also magnetic field, then you get, so these give you the magnetic force. So what we learned so far was magnetic force on a single charge, positive or negative, and it was QVB times sine theta. Now let's move to magnetic force on a wire. This time we have some background magnetic field again, but instead of single charge, now we have a wire where there are, in the case of electric current, we have negative charges which can move. Now from here, so instead of Q, if you remember from earlier chapters, the current is amount of charge passing through the wire per given time. So instead of Q here, I can write I times T, or delta T. And instead of velocity, I can write, so let's say this cable has length L, and if a given charge passes through the cable of length L, let's say it goes from here to here in time t, then I can find the velocity by dividing the length by t. And I'm going to keep b and theta the same. Now instead of v, I have the current here. So this theta will be, let's say there's some magnetic field. This theta is now the angle between the wire or the current and the magnetic field. Now if you look at here, these delta t's, they cancel each other. So what's left is I LB times sine theta. So when we have single charge like these, then we are going to use this equation, this formula. But when we have a wire like this, then we will use this equation. But you can derive these one from another, so they're in principle the same equation, but for wires we have to use this one. So the right-hand rule is still valid, but instead of V, now we have, for the index finger, we have current. And if you have, let's say, it's set up like this, so there's a bar magnet here. So this is the north pole, this is the south pole. So that means the magnetic field is in this direction here. And now there's a battery here, so there will be some current, and the switch is closed, so there was some current. The current direction is from positive pole to the negative pole. Now, if you look at here, so the current is in this direction, which is shown here with green color. The magnetic field is to the right, which is shown here. So from north to south. And now use your right hand to find the direction of force. So your index finger points this way, your middle finger points this way. So this is middle finger, this is index finger, and your thumb will show you that the magnetic force on this wire in this setup is in the downward direction. So this is your thumb. Okay, here's an example, a horizontal wire, which is here. So this is the wire. It has current I on it, carries current, and is in a vertical magnetic field. Magnetic field lines are in the up direction. What is the direction of the force on the wire? Now your index finger points to the right. Your middle finger points to up. And if you do that, what you will find is your thumb will be pointing out of page direction. So the answer is for the force is out of page. Okay, what about this situation? Now in this case, B and I, so your index finger is in up direction. Now you have to keep 90 degrees between these fingers all the time, okay? Now, how can you have index finger and your middle finger, which here magnetic field and current are they are in the up direction? How can you have these two fingers point in the up direction and also keep 90 degrees in between? Well, that's impossible, right? Or in other words, if you write down the formula, now there's the sign. In this case, you have what is the angle between them? Well, it's 0 degrees. And sine 0 is 0, so in this case, force is 0. So you can't even, it's not possible to point these two in the same direction, and if it happens, then you have sine 0, which leads to that force is 0. Okay, so now in this setup, what we have is we have a battery that it's connected to this metal with wire. So there's current that comes out from positive and it goes into the negative. So here's the current on this metal. It's flowing to the right. And the magnetic field lines are into the page. Now in this case, we have also gravity. So if you have this, so basically a current carrying rod of length L, this one, and mass M hovers in air due to the uniform magnetic field of strength B. So this piece of rod, it's metallic rod, it's in this setup, is hovering in air. So what should be the current so that the rod hovers in air without accelerating up or down? So we don't want it to go up, accelerate up, or fall down. What should be the current? Well, what keeps it in air is the balance. It's because of there's gravity in the down direction. So the only force that can balance it here is the magnetic force, right? And it should be in the up direction to balance the weight. So we equate them to each other. Weight is mg, and the magnetic force on the wire, in this case we have this rod, by that occurs when there's a current and the magnetic field. So we write the formula that we learned, IBL. Now what is the angle between this current here and the magnetic field? Well, current is to the right. Magnetic field is into the page. So the angle between them is 90 degrees, which gives you 1. So what we have here is then IBL equals mg. And if you solve for I, because here it asks what should be the current so that the rod hovers in the air without accelerating. So in this case, if you solve for I, it turns out that it's equal to mg divided by lb. Again, L is the length of the rod. So magnetic field magnetic fields, magnets, and their interaction with the wires. They are used in real life. For example, if you look into a loudspeaker, what you have is you have a wire, okay, and current goes through that wire, and there's also this magnet. And this wire is connected to this diaphragm here, which can move in and out. So the diaphragm moves in and out because this wire moves in and out. Now what we learned, if there is current in the wire, and so the wire has some length, and if there is magnetic field, which is in this case created by the magnet, then there's force on this wire. So there will be magnetic force on this wire, and that force, it will come and go, and it will move this wire, the coil, and in turn that wire is connected to the diaphragm, so the diaphragm will move in and out, and it will create sound. So this is how sound is created. So the player, the music player, or any audio player feeds the loudspeaker change in current. So the current is not constant, it changes, comes and goes, modulated, and it's modulated by the audio recorded. It could be a music, it could be sound of a person, whatever it is. So that modulates the current. So the current goes up and down depending on the audio recorded. And what happens if the current changes? Well, the magnetic field is constant. It's coming from the magnet. But the current changes, so the force changes, right? So the magnet and the current on the coil, they create a magnetic force on the coil. The coil moves, vibrates the diaphragm accordingly, and the music is heard by the person listening to this loudspeaker. So basically, again, the recording makes the current change according to the recording. It could be music. And since the current is changing in time, the force is also changing. So then this going in and out of this diaphragm, it changes and it produces the sound according to the recording. So this is how a loudspeaker works. Now let's move to loops of current and magnetic torque. Now we have a scheme of electric motor. So in electric motors, what you need is, so here's an example. There's usually a coil and magnet. So in this case, the coil is here. Of course, it has several turns. Here, only one turn is shown, but in principle, it has several turns. And you also have magnets. They produce constant magnetic field. So in this case, north and south, you have magnetic field in the left direction. Now, if you connect this motor to a battery, so you will create current. Current comes out of positive pole. So it goes like this, and here, this is the current direction. So it goes like this, and here, this is the current direction again. Now, use your right-hand rule here to find the direction of force. If you use it here, so the current is, this is current direction. Magnetic field is to the left, and if you use your right-hand rule, you will find this part of, so this part of the wire, it feels the force in the up direction. When you come to this part, the current is now in this direction. Magnetic field is again to the left. And the right-hand rule gives you the force in the down direction. So this part feels force in the down direction. Now this part here, the current is this way and the magnetic field is this way. Now they have the angle 180 degrees. And what is sine 180 degrees? It's 0. So there's really no force here. So here the force is 0. Also these small pieces, there's no force. So the force is only here and here. But importantly, the direction of the forces are in the opposite direction. So what happens? Well, this will turn, right? So this coil will turn in this direction. So what do you get? So you have a battery, so potential source creates current, and you have constant magnetic field created by these magnets. And by these, what you build is an electric motor, which turns, in this case, in this direction. So when we talk about the power of electric motors, we usually give it in terms of torque. So it means you can think of it as rotational force. For example, for this Tesla model, it produces torque. Its motor produces torque 660 Newton meter. So that's the amount of torque this model's electric motor produces. So let's go back to Physics 1, Chapter 11, and let's remember what torque was. So we need force to push things. So if you have a box, if you want to push it, then you would apply a force, which is a linear thing. But we need torque to turn or twist things. If you have let's say a bicycle wheel, if you want to turn it, you don't push it. You apply a force like this and it will create a torque. So you apply a force and it would create a torque. So torque is a rotational force. And torque depends on the force, so it depends on force, but it also depends on the distance between the rotation axis and the point where the net force is applied. So in these two cases, you have the wrench, and so here's the bolt. So you want to loosen it, let's say. Then, so if you apply a force here, the torque that this force creates would be the distance from this point to here. So it's R2. It will be R2 times F. But if you apply the same force at the end of the wrench, so this distance is R1, so it will be R1 times F. So this torque here is greater than this torque. Notice that we use the same force. Let's say this is the amount of your force that your arm can provide. We're using the same force, but we are getting different torques. What is the reason for that? The reason is that torque not only depends on force, but it also depends on the distance. So that's why, and of course, the effect is different in these two cases. In this case here, if you push it from the end, you get a larger torque. And that's indeed why we hold the wrench at its end. We never hold the wrench here. We hold it or push it from its end because it creates more torque. So that's why in rotational problems, we don't talk about force, because you can see that the force can be the same, but at different points, it has different effects. So instead, we talk about the distance times force, which we call torque. Now, the convention for the directions of the torque is if it's clockwise, it's negative, and if it's anti-clockwise, it's positive. So for the force, for example, you can define a coordinate system as this way positive, as this way negative for linear case. And for the rotational, these are the definitions. Of course, these are just conventions, just like the coordinate systems, but you can use this definition. So the torque is the general formula is R times F times. There's also sine theta, and that theta is the angle between R and F. In the case of this example, the wrench, we have not used the sine part. Well, we actually used it, but we haven't written it here because the angle between the force and these radius vectors are 90 degrees. So that's why we haven't written it explicitly, but if you want, there is sine 90 and sine 90 here, which is 1. Okay, so here's a quick example on the torque. The question here is, what is the net torque around the center? So we have this bicycle wheel fixed at the center. There are two forces. One of them is at 90 degrees with respect to the radius. The other makes 50 degrees with the radius vector, which is here. So how do you write the total torque? Well, you first write the torque, let's write the torque due to this vector. So you write the force, you write the radius, which is 0.5, and you write the sine of the angle between them, which in this case sine 50. And also this force, it would turn the wheel in this direction, right? And this direction is counterclockwise, so it will be positive torque. That's why we have positive sign here. Now let's come to F2. So the torque will be 0.5 times radius times the strength of the force. And now the angle between them is 90 degrees, which will give you 1. Now, is it positive or negative? Well, this force, it would try to turn the wheel in this direction, and that direction is clockwise. So that's why it contributes a negative sign here. So if you do this algebra, you find the torque to be 0.75 Newton meter. And the resulting, or the net torque, is positive. That means this wheel will turn in the positive direction, which is in the counterclockwise direction. Okay, so now we talked about electric motors. So we have a wire like this. Okay, so it's connected to a battery, but it's not shown here. Let's say this wire is fixed, so it can turn around these 2 points. So it can turn this way or this way. Let's say there's a current that flows on the wire. So this is the direction of the current. And again, that current is created by some voltage source, which is not shown here. And let's also say there is a magnetic field. So in this region, the magnetic field is into the page. In this region, it's out of the page. Now, for this part of the wire and for this part of the wire, the current direction and the magnetic field direction, they are 90 degrees. So normally you have sine 90 here, but you don't have to write it, it's 1. So as per this formula, the force here on the side is IBH. Originally it was IBL, but in this case, the length of this part of the wire is H. So that's why we have IBH, and here the force is also IBH. Now these short parts, they don't feel any magnetic force. Why? Because here the current and the magnetic field, they're in the same direction, so you get sine 0, and down here the current is to the right, the current is to the left, the magnetic field is to the right, so you have 180, but in each cases you have sine 0 and sine 180, it gives you 0, so the forces on these short sides of the wires, it's 0. So we only have force on this part and on this part. The magnitudes are given here, and the direction of the forces are given. Okay, I misspoke before. I said these are the direction of the magnetic field. These are actually the directions of the forces. The magnetic field direction is to the right. Now, how do you find these directions? Again, use the right-hand rule. So index finger shows the direction of the current. Here, for example, the current is in the up direction. Here, it's in the down direction. Magnetic field lines are in both cases. They are towards right. So that will be your middle finger. And if you use your right hand, you will find the force here on this part of the wire is into the page, and the force here is out of the page. So the force on this part of the wire. Now, so as I said, this rectangular wire, it's fixed at these 2 points, so it can rotate. It can rotate around this axis. So what do we have for rotational problems? We have torque. We talk about torque. So we have force and we have some object that can rotate around a fixed point. Then we write the total torque. Let's do that. So for this part, so there will be, so there's a force here and there's a force here. Now, if you think about it, those two forces, so this is the side view. Let's look at from the side. So this part, so on one side, of the long, so the side view is, you can think of as looking at from here, or it's actually more like, so this part is this part, so the force is up, and this part is force is down. Now, this distance is W, so the distance is then from here to here is W divided by 2, same thing here. So the axis is here, so these are the radius then. So the radius is W divided by 2. So if you want to write the torque for each forces, now they are trying to rotate this loop of wire in this direction, same direction, which is counterclockwise. So I will write torque for both of them, and I will use a negative sign for both of them because they are trying to turn it in the counterclockwise direction. Now, what is the radius for each one? It's omega W divided by 2. The current is the same for both. The magnetic field is the same, and the length of the wire here is the same, which is H. So I have H here. And in each case, you can see that the magnetic field and the force, they have 90 degrees. So we have sine 90. So the total torque here is, so we have 1/2 here. So they add up to 1. So it will be negative IBH omega. So here it is. And instead of H omega, so if you multiply by H and omega here, what you find is the area of this loop, right? So this is the area. So instead of W, I can write just A. So the net torque in this setup is negative IBA. Here, negative sign is not really important. It just shows the direction of the torque. But what's really important here is the magnitude, which is IBA. Okay, so what about this situation? Let's say the loop turned a little bit and it now came to this position. Now, in this case, again, the force is up. You can use your right-hand rule. Magnetic field lines are to the right. Current here is towards you or into the page at these points. And you can use your right hand and you can find the force should be up here and down here. Now, the only difference here is we will write the same equation the same way we will write the torque. So this is basically R, this is basically F, and we have the sine theta. So the difference is here, the theta is not 90 degrees anymore, so we have to leave it as theta. So in this general situation, then the answer is IBA sine theta. And if you put 90 degrees here, it gives you 1, which you end up with IBA, which was the result here. So you can get back to this if the angle is 90 degrees. But in general, this is the answer. So this is the torque, net torque on this loop of wire because of the current and the magnetic field. Now let's write the most general formula for the magnitude of the torque exerted on the loop of area and n turns. Here we have just one turn. So the cable, we have just one cable or wire, just one turn. In this case, n equals 1. But you can in principle have multiple turns, which will look like this coil in real life. And for each turn, you will get an extra so for each turn, you will get this much torque. And if you have n turns, then you would multiply it by n. So if you have n turns, this coil, there will be n times more torque on this coil because it has n turns in comparison to this coil, which has just one turn. Okay, so this formula here is then the torque exerted on the loop of area A, so area here is the area here, and n turns. Okay, what are the applications of these loops? What happens when you have a loop which has current on it and when there's a magnetic field lines? When you put it in the magnetic field, which is created by magnets here, and you have the coil, and what happens when current passes through that coil? One application is the electric motors. We talked about it in the previous slide a little bit. So you have the coil, there's a magnetic field lines from north to south, there's a current, and there's a constant, there's a force all the time that we mentioned before. So it is these forces that creates torque, and that torque turns this coil, and in turn you can connect it to a car or anything so that it creates mechanical force, so mechanical work. Here you can see an example of cell phone vibration motor. It's small, but it could create, it's enough to vibrate your phone. And again, as we mentioned, power of motors are reported in terms of torque. So we will come back to electric motors in more detail in chapter 23. But for now, so that's all for electric motors. And the other application of this coils and current carrying coils and put in magnetic field, one application is here. The torque on a wire or coil is proportional to the current. So the torque on this wire, F, created by F, it depends on the current, right? ILB. And the torque, so multiply this by R, you get the torque. So the torque also depends on I. So if you run more current, then you get more torque. So then you can measure the current by looking at the torque on that wire. So this is how ammeters work. So ammeter is, remember, if you have a circuit which is connected to a battery, if you want to find the current, then you will connect it to an ammeter, which would measure the current. How does it do it while the current passes through the coil. There's coil inside the ammeter. And since there's also a magnetic field created by these magnets, and what happens? Well, this coil will feel some torque, and that torque will twist. It will twist this coil. So, and that coil is so that this piece of metal, it's also connected to a spring. So it's not free to coil. The coil is not free to rotate easily because it's connected to a spring. So spring is it resists to the rotation, but still it can rotate it a little bit. And that amount of rotation that's coming from the torque, which is coming from the magnetic effect, you can read the amount of rotation because of that torque on the scale, and that scale will give you the current. If you run more current, there will be more torque. Look at this equation. More current, more torque. And if there's more torque, even though there's the spring, but you can move this needle, which is on the scale, to you can twist it more, and it will show you the amount of current. So these are some applications of torque in these setups. Okay, let's move to section 6. So that's about how the magnetic field is created. So far we have learned this. A charged particle or current in a wire would feel magnetic force. If it's a charged particle, it's this. If it's a wire, we would use this when it's placed in a magnetic field. But we were not concerned what created magnetic field. So we never mentioned what creates that magnetic field in the situations that we analyze. So let's now, starting with this section, understand what creates the magnetic field. Well, here's the answer. Movement of charged particles or electric currents, which is the same thing, in wires, they create circular magnetic fields. So if you have a wire like this, and if you run a current, then this current, it will create magnetic field lines around that current. So these are the magnetic field lines, like this. Of course, you can also create magnetic field lines by using a magnet, but this is the other option. You can also, so without a magnet, if you have a current carrying wire, there will be magnetic field lines. So any wire that carries current, it actually creates magnetic field lines around it. So any wire that you can see right now around yourself, if there's current passing through them, then there is magnetic field around those wires. And how can you test it? Well, if you have a compass at home or with you, then take it out and try to get it closer to a wire. And you will see that it will be deflected. The needle will be deflected by the magnetic field that's created by the current on the wire. That's actually how all of these, the effects of magnetic fields and the currents, were discovered in the first place. So the direction of the magnetic field created by an electric current is determined by the second right-hand rule. What should be did? So we said the current creates magnetic field, but is it going to be this way or this way? Now, the way to find it is what's called the second right-hand rule. Now, how it works, it point the thumb, your thumb, of your right hand. Again, you have to use your right hand along the wire. This part is important, in the direction of the current. So your thumb should be in the same direction as the current. Now, the second part of the procedure is curl your fingers around the wire. Here you go. You curl your fingers around the wire. Now, your forefingers are showing the direction of the magnetic field created by the current. So your fingers show this direction. So the magnetic field lines are in this direction, which is shown by here these red vectors. So this is how you find the direction of magnetic field lines by a magnetic field direction by using your right-hand rule. Magnetic field is tangential to the circle shown in the figure. So you can see that the magnetic field lines are tangential to the circle that's drawn around the wire. Of course, magnetic field lines, the vectors or magnetic field is not created only on this circle shown. There are actually magnetic field everywhere. Even there is also at these points. But the point here is they are tangential. So they are tangential. And also they go on a circle. Now compasses placed around the current carrying wire show the direction of magnetic field produced by the wire. As you can see here, the magnetic field lines here, they go in this direction. And you can see that the arrow of the compass, they show the direction of the magnetic field lines. If you have any compass at home, you can actually try this experiment at home. Okay, here's an exercise. If the currents in the wires have the same magnitude but opposite direction. So we have two wires here. Okay, we see the cross sections of them because they are going into the screen and coming out of the screen. So this one is coming towards us. This one is into the page or screen. So we have two wires. The question is, what is the direction of the magnetic field, the total or net magnetic field, at the middle point? Now, you have to use the second right-hand rule, which is shown here. Now, for this one, imagine that you curl this wire in a way that your thumb points out of the screen towards you. And if you do that, you will find that the magnetic field lines will be in this direction. So at every point around this, even this wire will create magnetic field lines here like these. But what's asked about is this point, the middle point. So at this point, the magnetic field that's created by this wire here will be in down direction. So what about this one? Now, again, imagine holding this wire in your palm in a way that your thumb now is in the direction of into the page direction. So in this case, you will find the magnetic field lines created by this wire. They are in these directions. And at this point, at the middle point, it will be again in the down direction. So both of them are down direction. And if you add them up, you will get a vector again in the down direction. So the correct answer is direction 3. Okay, let's move to Ampere's law. It relates the magnetic field around the wire to the current in the wire. So we learned that the magnetic field lines will be, we learned about their direction, but what will be the magnitude? What will be the magnitude at this point? What will be the magnitude at 1 meter, at 2 meters? In fact, the magnitude will actually go down, and it's greatest when it's close to the wire. But what is the formula for the magnitude? Well, Ampere's law, it tells us the strength of the magnetic field around the wire. We skip the derivations here, and the result is this one. So the magnetic field created by a current in the wire is given by this formula. And there's 2 pi in the denominator and r. R is the distance from the wire to the point where you want to calculate the magnitude of the magnetic field. And here mu0 it's a constant of the universe that we live in. It's 4 pi 10 to the negative 7 Tesla meters divided by amperes. And it's called permeability of free space. So let's put this formula in use. In this exercise, what we have is the magnetic field created by current I is shown. So we have this current carrying wire. Now in this problem, the magnetic field is not, produced by other agents. It's created by the wire. So what you see here, the magnetic field, it's the wire's magnetic field. And you can see that if you wrap your hand so that your thumb shows in the direction of the current, you will find in this region, the magnetic field lines are out of the screen towards you. So that will be your 4 fingers. And in this region, the magnetic field lines would be into the screen. Okay, so we have the charged particle here. The question is, find the force on that charged particle. So it has the charge, it has the velocity, and there is some background magnetic field that's created by this wire. So the formula for the force on a charged particle, it's charge of the particle, velocity of the particle, and the magnetic field. And the sine theta is the angle between v, the velocity, and b. So in this case, the b is into the screen, v is to the right, so it's 90 degrees. So here we will have 90 degrees. Now, what is that b? So let's keep q and v here. Now that b is the magnetic field created by this wire. And for that, the magnitude of it is given by this formula. And so instead of b, we will substitute this part. So it will be mu0 I divided by 2 pi r. So again, this is just 1. And so this part becomes this. So this is the force that this charged particle feels, the magnetic force, when it has the velocity v and when it's placed at a distance r from the current carrying wire when the current on the wire is I. Okay, so in this exercise, we have a positive charge moves parallel to the wire. So we have a wire that carries current I, and there's a positive charge particle here, which goes in the same direction. So they're parallel. If the current is suddenly turned on, so there's now current on this wire, in which direction will the magnetic force on the positive charge act? So what will be the force direction on this charged particle? Well, to be able to find force, remember force was Q VB, and we would use the right hand rule here. So we know V direction, but to be able to find force direction, we have to know the direction of the magnetic field. And who creates magnetic field here? Well, it will be the magnetic field because of this current carrying wire. Now, the question then we have to think about first is, what will be the direction of the magnetic field at this point because of this current? Well, for that, we have to use the second right-hand rule. So now look at the wire. The current is in the up direction, and use your right hand. And so it turns out at this point, the magnetic field will be out of page. So it will be out of screen. So that will be the magnetic field. Now we know the magnetic field direction, we know the velocity direction. Now we can find the direction of force. We're going to use the first right-hand rule here. So your index finger is in the up direction. Your middle finger is it's out of page because magnetic field is out of page. So it turns out that your thumb shows this direction. So that's the magnetic field, magnetic force. And that is actually the question. Now, but you have to check, do we have a positive particle or negative particle? Because if you have a negatively charged particle, you have to flip the direction of a force that you find from the right-hand rule. But in this case, we have positively charged particles, so that's the correct force. So whatever your thumb gives you, it's the correct force direction for a positively charged particle. So it turns out the force is in the positive x direction according to this coordinate system. Okay, so now, so we talked about in the previous slide and the previous questions, we had a charged particle and a wire, okay? Now let's move to the case where we have two wires and both of them, they carry current either in the same direction or in opposite directions. So if we have two current carrying wires, wire 1, so one of these here, and wire 2, let's say this one, wire 1 will feel a magnetic force due to the magnetic field created by wire 2. So this wire 2 creates magnetic field everywhere, including this point. And since there's current on this wire and the magnetic field, which is created by wire 2, now this wire 1 will feel force, how much? It will be IBL. Now the same thing applies to wire 2 as well. Wire 1 will create magnetic field here. Wire 2 also has current up or down. In either case, it will feel force 2. So these two, then they will feel force because of the magnetic field that is created by the other wire. So what happens when you run current in both of them? So you turn on the switch in one way, so they repel each other or they are attracted to each other. So in one case, the currents run in parallel, like the same direction, and in the other case, in the other position of the switch, the currents run in opposite directions. So let's see which affects the attraction or repulsion happens when. When you have parallel currents, they attract each other. So if the currents are parallel, which means in the same direction, then they will attract each other. When the currents are anti-parallel, which means they're in the opposite directions, they will repel each other. So, for example, if you want to, let's look at the parallel case. So let's calculate the force on wire 2. Okay, so this force. So there is I2, L, so it's the length of this wire, and also the magnetic field here. So if you want to find the force on this wire, you have to do I, L, B. I is the current here, which is I2, L is the length, and B is the magnetic field. But who creates this magnetic field? Well, this creates its own magnetic field, but it's not affected by it. But this magnetic field that affects this wire 2 is actually created by wire 1. And what is the direction? So this is actually B1. So this wire, there's current here. Now use the second right-hand rule. Your thumb shows right to the right direction, and you curl with your fingers this wire, and you find that the magnetic field created by this wire at these positions, they are into the page. So these are B1, they're into the page. And what is the magnitude of that magnetic field? Well, we learned the formula. It's given by this formula. So here there's actually R, but in this case, it's the distance, which is, you can use either R or D, it doesn't matter. So it's basically the distance. So we are interested in the magnetic field created on this wire, created by wire 1. So it will be this distance D. And it turns out this is the magnitude. But what is the direction? Well, now let's find the direction by using the first right-hand rule here. Okay, so the first right-hand rule, there was I for index finger and B for middle finger. So your middle finger here shows into the page. Your index finger shows right direction. And if you do that, you will find that your thumb shows in the up direction. So this wire will feel force in the up direction. Now, do the same, follow the same reasoning for wire 1. Now, this wire 1 will be affected by the magnetic field created by wire 2. And use the second right-hand rule for wire 2 to find the magnetic field, direction of the magnetic field that it creates. Turns out on this wire, the direction is out of the screen. Now you have current in this direction. Now we are going to use the first right-hand rule. The current is to the right, the magnetic field is out of the screen, and your thumb will show down direction. So this wire is pulled down, this wire is pulled up. By the way, forget gravity, there's no gravity here. So the result is these wires will come together like this, so they will attract each other. Now you can do the same reasoning here for the opposite currents in the opposite directions, and you will find the direction of the forces to be in these directions, and you will find, so this leads to repulsion between the wires like this. Let's go back to this demo once more. So in one case, of course, here we don't know the directions of the current, but we can see that they repel each other or they are attracted to each other. And that depends on if the currents are parallel or if they are anti-parallel, which means opposite. Okay, now let's move to current loops and solenoids. Magnetic force at the center of a current carrying wire loop. So if you have a wire loop like this, so basically a wire that's put in a circular shape. Now this is the positive terminal, so the current goes up like this and then goes down here to the negative terminal. When you have this, you can use the second right-hand rule at different points, and you will find it creates, this current creates magnetic field lines in these directions. The magnetic field at the center of the loop is given by this formula, mu0I divided by 2R. Now, because that we are talking about the center point, it only depends on the radius of this loop, so that will be the radius here. Of course, at different points, B will be different, but this formula is only for the middle point. And N here is the number of loops. So here we have just one loop. but in general, you can have a coil like this. And finally, if you look at the direction of the magnetic field lines, they go this direction and then come back. It actually looks like, almost like we have a bar magnet where this is the North Pole and the South Pole. And from the North Pole, the field lines go out and they go in to the South Pole. So it is as if having a bar magnet at the center of the loop. So this is good because if you have a bar magnet, you cannot turn it on and off, right? It creates magnetic field lines. There's no way to turn it on and off. But the good thing about the loop that's connected to the battery, with a switch, so you can have a switch here. You can have a switch, connect the switch here. You can, turn it on and off so that you can have a magnet that can be turned on and off at will. So that's the good part of these electromagnets. So these are called electromagnets because they're created by not the material like a magnet, but they're created by current. So current carrying wire loops act as if bar magnets. We talked about this. So what happens if you have two of them that are at a close range? Now, if you have, let's say, if you run current on this one in this direction and on this one in the same direction, what happens? Well, so use your right hand, the second right hand rule. You will find these will create magnetic field lines in these directions, and this is the same direction. Okay, just like this. And now instead of these magnetic field lines, you can forget about them, but you can place bar magnet. So these bar magnets are not real here. They're just put to show the direction of the magnetic field lines created by this current. So now instead of this setup, you can think of there is a bar magnet like this, north and south. Why do we put north on the right hand? Because again, use your right hand. Let's go back to this slide. If the current flows in this direction, it creates magnetic field lines this way. And it corresponds to the situation where the North Pole is here, if you have a bar magnet, and the South Pole is here. Okay, now you can forget about this setup. So instead, you can replace it by a magnet. Again, there's no magnet here. It just shows you the direction of the magnetic field lines. And you can, again, this is the same thing, S and N, situated like this. So now forget about this. So what happens if you have two bar magnets positioned like this, north and south? They're close to each other. What happens? They will attract each other. So the bottom line here is, if you have two loops and if the currents are in the same direction, what will happen? They will attract each other. Now, what happens if you have two loops that at a close range, but the currents are in opposite directions? Well, again, this one will create south-north, but this one, use the second right-hand rule. The current now flows in this direction. Wrap this wire at different points with your four fingers in a way that your thumb shows the direction of the current, and you will find the magnetic field lines to be this direction. So these are the magnetic field lines. And this corresponds to, if you have, instead of this circle, if you want to put it, if you want to show it with the overall effect by a bar magnet, then you would put north here because of the magnetic field lines, their direction, and south here. Now, the situation here is different. We have north, south, south, north, north, south. So like poles that are close to each other, what will happen? They will repel each other. So when the currents in opposite directions, then you get repulsion. That was actually the case also in this parallel, when you have parallel wires. If the currents are in opposite directions, then you get repulsion. So they will repel each other. The same thing with the loops. When the currents are in opposite directions, they repel each other. So once more, the magnets shown here are not real, so there are no magnets. They are only put or drawn just to show the direction of the magnetic field lines created by these currents. So they only represent the induced magnetic fields by the current carrying loops. Okay, now let's move to solenoids. So solenoid is used as an electromagnet. So it's a magnet, but you can turn it on and off electrically. So it works with the current. It's not a material, it's not a bar magnet. It acts as a bar magnet because of the current, it creates a magnetic field inside. But the nice thing is if you turn off the current, then the magnetic field lines go away. So electromagnets run on electricity, current. Magnetic field inside a solenoid is given by this formula. The amount of the magnitude of the magnetic field inside within the solenoid, it's mu0. Remember, it was the constant, the permeability of free space, and number of turns n. So how many turns do you have in this coil? So in this case, 1, 2, 3, 4, 5, 6, 8. So you would count it, all the turns. L here is the length of the solenoid here, and I is the current that passes through that wire. So n divided by, so uppercase N, number of turns or loops, divided by length, it can be written as lowercase n. So sometimes in problems, only in the lowercase n is given. It would be number of loops per meter. So in that case, you would use lowercase n. And that, as you can see, the magnetic field in a solenoid, it depends on lowercase n or uppercase N divided by L. Mu0 is just a constant. You can't change it. It's the constant of the universe. So practically it depends on n and also current. So if there's more n or more current, then you would get more magnetic field. And what is the direction of magnetic field lines? Well, inside, you're usually interested in inside or at the front of the solenoid, the magnetic field lines. Again, you can find the current direction from in this figure. It's this way, so here this way. You can wrap the wire in a way that your thumb points in the same direction as the current, and your fingers, the curling direction of your fingers would show you the direction of the magnetic field. For example, if you curl here, so here the current is in this direction, you will find inside the magnetic field is this way to the right, and outside it's to the left. And these electromagnets are really used in diverse areas. For example, you can have a solenoid valve like this. So there's water here. Water gets in and water gets out if this is open. So this basically has a coil inside. And there's also some metal. So you can turn this coil on and off. So you can move the valve inside up and down to let the water flow or to block the passage of water. So this is basically a solenoid or electromagnetically controlled valve. Now, in this last section, we will talk about magnetism in matter. So now let's move from magnets back to the materials. So some materials, the magnets, they are magnetic, they produce magnetic field. Okay, but some don't. For example, if you hold a piece of iron or nickel or any other metal or insulators, doesn't matter. Most of them, they don't create magnetic field. But some special materials, magnets, they create magnetic field. And how does that happen? So how do bar magnets create magnetic field? Now what we have is, so in each atom within the material, within the magnet, or any material, doesn't have to be magnet, there's a nucleus that's positively charged. There are protons and neutrons in the nucleus. And there's the electron outside. So the electron has some, of course, this is a classical picture, but that picture explains the magnetism to a certain degree. So the electrons, they have some velocity. Now, if the electron is going around in this direction, remember the current is defined as the opposite direction to the negative charges. So it's more like, so the current defined as in the opposite direction of the electrons. So if the electrons are rotating this way, conventionally, it's just a definition, historical definition of current. The current is in this direction. Now, what happens if you have a current in the loop? In this case, the electron of the atom. Well, if you have a current in the loop, then that loop creates magnetic field, right? Of course, there's no magnet within the atom, but the atom itself acts as a magnet. Why? Because the current or the movement of electrons, they create a magnetic field. Because they have velocity, they have charge, so they would create magnetic field. Or in other words, they have a current. When there's a current, then there's a magnetic field. So then each atom, they actually act as magnets, right? So each atom within the material, they act as a magnet with north and south poles. So the electrons spin and orbital motion. So there are two effects that contributes. The electrons are charged particles. They go around themselves. They have a spin. So a charged particle, or you can think of it as a local current. And they also go around the nucleus. So that's the orbital motion, orbital current. These two effects, they create magnetic fields, as you can see here, within the atom. So consider each atom as an atomic scale bar magnet. Now let's get back to the question, why do some materials are non-magnetized, but some are magnetized, like magnets? In non-magnetized materials, the magnetic field from each atom is in random direction. So we said, you have a material, so let's show south and north as a vector like this. So in each material, so you have a material, it has atoms, and each atom is a bar magnet. Their north is showing in different directions. What happens if the directions of the magnets or atoms, if they are random? Well, if they are random, the magnetic field they create will be in all directions. And when you take the average, on average, there will be no magnetic field. So globally, there will be no magnetic field, even though each atom creates magnetic field. But because they are random, they cancel each other or average out to zero. These materials are non-magnetized. But in a magnetized materials, like such as a bar magnet, almost all magnetic fields from each atom point in the same direction, so that the magnetization in macroscopic scale arises. So this was a non-magnetic material. That means it creates no magnetic field. But if you have a bar magnet, like here, so now you have a bar magnet. Now what happens is within that bar magnet, the atoms, they all aligned, their magnetic fields, they are all aligned in the same direction. Of course, this leads to globally, if you add these vectors, it will give you a large vector. So it will give you a non-zero B, non-zero magnetic field. So that's the difference between non-magnetic and magnetic materials. So they're not in principle different. The only difference is bar magnets, let's say magnetic material, is that the direction of the atoms, the direction of the magnetic field produced by those atoms, they are all point to the same direction, which leads to a large, they add up to give you a large magnetic field in that direction. Okay, finally, let's talk about three types of magnetism in matter. First of them is ferromagnetism. Ferro means iron, but it's not specific to iron. It can be iron, nickel, but it's not valid for all metals. It's valid for some metals. So they have local magnetized domains. So there are some domains where the magnetic field lines, they add up in the same, so the atoms, they point in the same direction, their magnetic field. So locally, you get magnetic field lines in the same direction, but it's not global. If you look at it globally, it's still random. So iron, it's not magnetic, right? It doesn't attract metals. But when an external field is applied to a ferromagnet like iron, they become permanently magnetized even after we remove the external magnetic field. So you can make this experiment at home. Let's say you have a bar magnet and you have a piece of nail, let's say, which is iron. So when you approach these, when you get these together, so you can touch the nail with the bar magnet. So what will happen is these domains now will point in the same direction because of this bar magnet, the external magnetic field. Okay, once they point in the same direction, now even if you get rid of the bar magnet, this nail now will be magnetized. So it will now, after this point, it will attract metals. So now it becomes a magnetized material. And even after you remove the external magnetic field from the bar magnet, it will still stay magnetized. So these type of matters, they're called ferromagnets, and iron is one of them, nickel is the other one, but not all metals act like it. Now the second type is paramagnetism, and the example is aluminum. Normally non-magnetic, just like iron, but becomes magnetized with external fields. So you have a piece of aluminum and you bring a bar magnet. Now it becomes magnetized just like iron, but it loses its magnetization when the external field is removed. So when you remove this bar magnet, it doesn't stay magnetized as iron. It loses its magnetization. So the difference between ferromagnetism and paramagnetism is that if once you magnetize the iron, it stays magnetized, even if you remove the bar magnet. So that's ferromagnetism. But in the case of paramagnetism, which is the example here is the aluminum, it becomes magnetized only if you have a bar magnet or any other magnetic field source in close proximity. And whenever you remove the bar magnet, it becomes demagnetized again, just like here. So it stops attracting metals. So that's paramagnetism. Now finally, diamagnetism. So all materials, even a frog or a strawberry, here you can see the frog, they show diamagnetism. So an applied strong magnetic field, so here there's a strong magnetic field here, creates an opposing magnetic field in the material. So let's say if that strong magnetic field is out of the page, now here we have a frog. The frog will create its own magnetic field into the page. And the interaction of those magnetic field lines makes the frog hover in air. So the frog here it hovers in air, and the frog is, by the way, it's alive and it's not affected. And that, this effect happens because of diamagnetism. So if you have strong enough magnetic field that you can apply, you can actually make other objects to hover in air, like strawberries, or even live animals like this. So that's all for this video. See you in the future videos and lectures.